Okay, so let's continue with our discussion of curvature of curves in R2 in planes. Okay, and so we discussed last time that we could have a curve indicated by R of S being the arc length. S is a very convenient parameter for the curve because in that parameter the derivative of the position is a tangent vector which is naturally normalized. Okay, that's stated here, r prime dot r prime is equal to 1. Differentiating that, we learned that the acceleration, r double prime, is perpendicular to the tangent, and we show that in the picture. Okay, so this leads then to the definition of the curvature of the curve. Kappa is usually defined as the absolute value of r double prime of s. Now in some of the books, and sometimes we'll use it, kappa will also carry a sign. Okay, and we'll get to that in just a moment. But in other books, you have to be careful about this, kappa is always positive. For a typical curve, kappa indicates how quickly the curve deviates from the tangent. Well, it's proportional to r double prime, so that's not surprising, and we'll show that quantitatively on the next poster. Okay, but at this point we see that we can understand that in a very simple way. Kappa is proportional to r double prime of s. A simple exercise that you'll be doing in the exercises is to show that for the case of a circle, for example, kappa is just 1 over the radius of the circle. So it's an indicative of how quickly the circle deviates from a tangent plane. Okay, it's indicative of the curvature. The smaller the circle, the larger the curvature, because the curvature goes like 1 upon r. You can go back to our parameterization of the circle in terms of sines and cosines. Be careful to write it in terms of not theta, but theta equals s, the arc length, over the radius r, right, in terms of s. Do the derivatives and see that kappa is 1 over r. That's our first indication, that curvature carries a dimension. This is very significant. Okay, curvature is not a dimensionless parameter, it's a dimensionful parameter, and it tells us in units how quickly the curve deviates from its tangent. Okay, so we'll learn a lot about that, and we'll learn more about curvature when we come to surfaces. Well, there's special cases for the curvature we want to understand. For example, if kappa vanishes, then it picks out straight lines in the plane. Okay. Well, we're going to write in general that r double prime is equal to kappa times n hat, the direction of the acceleration, a unit vector n hat, just to give the direction of the acceleration, the magnitude of the acceleration being given by kappa. Okay, so this is definition, and the textbooks, for example, the textbook by DeCarmo, the one that we're following, uses this definition, and it's very important. So take a moment to feel comfortable with it. R double prime, where the prime indicates differentiation with respect to arc length, is equal to kappa, the curvature, times n hat, the direction of the acceleration. And we know that n hat is going to be perpendicular to the tangent. N hat is perpendicular to r prime. Okay, the dot product is equal to 0, as shown in the picture here. Okay, now in most cases we're going to write r prime of s. It's a unit vector, and we'll write it as the tangent. Perhaps I should have put a hat over t instead of a vector under t, because just to remind us that it's a unit vector. Okay, but that's okay. Okay, so r prime, that's dr by ds. S is the arc length, and so that's a unit vector, and that points parallel to the curve. In the usual cases, we'll choose T and N to have the same orientation as I and J, okay, just to set up a coordinate system. And kappa is going to carry a sign and a magnitude as well. Okay. Now, what's the geometric interpretation of kappa? The curvature indicates how quickly the curve deviates from a straight line. Okay. In the case where kappa equal to 0, as discussed in supplementary lecture 9, which I hope you're following along with as we make the lectures. Okay, supplementary lecture 9. We take a moment and prove that if kappa is equal to 0, then r is a straight line, and also the converse. If r is a straight line, then kappa is equal to 0. Elementary stuff, but worth pointing out at this point. Okay. Now to show that kappa indicates how quickly r deviates from a straight line, well, we just use a Taylor expansion and look at how the position of a point on the curve deviates from a straight line as s increases from 0. So here I've just written the Taylor expansion of r of s. It's r at 0, first order deviation, second order deviation, third order deviation, etc., etc. Okay. And now I can do a little bit of algebra, okay, and look at the difference of r from r at 0, okay, and just plugging in the definition of r prime, okay, that's the tangent. Plugging in the definition of r double prime, that's just kappa times n hat, okay, and then r triple prime, well, that's just the derivative of r prime, which is kappa times n. And doing a little bit of arithmetic, I've indicated it here. Okay, r prime is the tangent. R double prime is kappa times n hat, the acceleration. R triple prime, sometimes called the jerk in mechanics books, is the derivative of kappa n hat. And doing a little bit of arithmetic on that, we can relate that to both kappa and kappa prime. And so a little bit of arithmetic shows me that the deviation of r of s from r of 0 is just equal to a bit that's proportional to t in the direction of the tangent, and then a bit which is in the direction of perpendicular to the tangent, the deviation from the tangent. Well, some of these terms are easy to understand. The leading term in r of s minus r is s times t. That's just from this term, s times t. And it just indicates that as you move along r of s, the leading order, you just move along the tangent by an amount which is just the arc length. The first deviation in the direction off the direction of the tangent is just given by this term in the Taylor expansion, 1/2 s squared r double prime. That's just 1/2 kappa s squared n. Okay, we get higher order corrections, and I've written them out here, although I'm not going to really need them, coming from the s cubed term. I get an s cubed correction to the linear dependence of r of s minus r of 0 in the t direction, and similarly in the n direction. Okay, so I can then make a plot of this graph, okay, and I can just say that I'll take my origin as r of 0, and I'll measure r of s off of it. I'll take t to be the x direction, n to be the y direction, and then plotting it here. Okay, I see that my lowest order term in the n direction goes like 1/2 kappa s squared. I've indicated that here. Okay, and that's what I want to learn from this exercise in the Taylor expansion. Okay, just how quickly does r of s deviate from the tangent? Well, the leading term is just 1/2 curvature times s squared. So the curvature, again, tells me how quickly the curve deviates from the tangent, and that's what I wanted to see. Now, in the recitation sections, we'll do some calculations in specific curves, and we'll show, for example, in the case of a circle, okay, that kappa is just 1 upon the radius of the circle. Okay, that's sensible. The curvature of the circle is just 1 upon its radius. Okay, the smaller the circle, the smaller its radius, the quicker it turns about, the quicker that it turns away from its tangent. Okay, the curvature carries a dimension. Okay, 1 upon r. It's not a dimension, full a characterization of that, and it distinguishes short distances from long distances. If you're dealing with a distance that's very small compared to 1 upon r, okay, then the circle is a very good estimate, okay, for your position, okay, and it shows you the deviation off of the tangent line very accurately. Okay. So we're going to think about these equations and ask the question, how do they generalize to spheres, and how do they generalize to general curved surfaces? Right? That's the whole point of doing, spending some time in R squared, in planes. We want to set up the questions that are going to then be generalized when we turn to curved spaces, symmetric spaces like the sphere, or the hyperbolic geometry of the Poincare disk. And then how does it generalize when we go to a curve that Gauss imagined, a curve where a curve on a space, okay, which has a general curvature called the Gaussian curvature K. Okay, so we'll start with a base space of R2, move to a base space of S2, the surface of a sphere, and then move to a base space, which is a general curve, a general sphere, a general surface, which has a Gaussian curvature that varies from point to point. Okay, so what is the generalization of curved surfaces? We're going to learn about the second fundamental form. It's going to control how fast a surface deviates from its tangent plane. So that'll be the generalization to higher dimensions from the exercise we've just done in 2 dimensions. Okay, that'll be interesting. It'll show us the visualization of the second fundamental form of differential geometry. The first fundamental form being the metric. We're happy with that. We understand that. The second fundamental form telling us how to embed a 2-dimensional surface into flat 3 space. That's the second fundamental form, and we'll learn about it later. Okay. Now let's turn to other topics in curves on R2 on flat spaces. And the first thing we want to turn to is the relationship between the curvature kappa and the turning angle of the tangent vector. So I might consider a closed, regular, simple curve like as shown here. Okay, it's oriented as shown here. It has a tangent vector t of s, r prime it is, and it has an angle off the x-axis which I call theta of s. Okay, and I just want to think about that, the concepts there in particular. Well, the first thing we note about the tangent vector is that it rotates through 2 pi as s of s goes around once. If we start at s0 and go all the way around here, okay, then clearly the tangent vector turns through the angle of 2 pi because it'll be, in this particular case, it's clearly bending in the counterclockwise direction, and by the time it comes back to S0, it's rotated once. It has to come back to where it started. Okay, it rotates through 2 pi to its left, and so I indicate that here, 2 pi. Well, I can parameterize T of S by just noting that it's a unit vector, T of S. I can write it as cosine theta in the x direction, cosine and sine theta in the y direction, it's unit vector, and then track theta of S and theta and cosine of theta and sine of theta of S as T rotates around, as the point S, as my point P moves from S naught all the way around the circle. Well, the closed curve. It's a closed simple curve. Simple meaning it doesn't intersect itself. Irregular and closed. Okay, you know what that is. So there's T of S. Okay, T of S is just cosine of theta in the x direction, sine of theta in the y direction. I can take the derivative of that with respect to the arc length S, and I get theta prime, and then a cosine becomes minus sine, sine becomes cosine, and I notice, okay, that I can pull out the theta prime from both terms. Okay, so it factors into a magnitude, theta prime, times a unit vector, and the unit vector n hat is of course perpendicular to the tangent. Well, here's the tangent, cosine sine. The unit vector n is minus sine cosine. Take the dot product, and you clearly get 0. Cosine sine minus plus sine cosine plus 0. Okay, so n hat is like that. And then I read off from my general relationship, my general definition of the curvature. Okay, in this case, that the kappa of S is simply theta prime of S. It's d theta ds. Okay, so we learned that the rate of change, okay, of the turning angle with respect to the arc length is equal to the curvature of the curve. Not very surprising, is it? Right? That's what we think about when we think about curvature. It's the rate of change of which the curve deviates off the tangent. Okay, I can integrate that expression around the curve. I imagine that this curve has a length L. So I integrate from 0 to L of kappa ds, and you see from this that that's just the change of theta around the curve, and that's just 2 pi. Okay, well this expression is simple, and you think, well, we're just belabeling the obvious. The reason I point it down and put it down here is the question. What happens to this relationship, okay, when the base space is curved? Okay, that's what we want to understand. Okay, we want to write down this expression again in the case of a curve on a curved space, okay, which has a natural curvature, and see how it changes. In that way, we're going to discover the Gauss Bonnet Theorem. Okay, and so we'll come back to this idea and use it later. Okay, it's a very significant contribution to mathematics. One of the most Gauss Bonnet Theorem has some of the properties which are so important that it leads, in fact, to the development of other mathematical disciplines beyond differential geometry. Okay, well, we'll get there when we get there. Okay, well, there are other things to be said and to be recalled about the geometry in two-dimensional flat space. One of the things we always learn about two-dimensional flat space is the geometry of triangles. We learn all these theorems about congruent and similar triangles. Well, how do you make a triangle? Well, you just take 3 straight lines and form a triangle. Okay, that's trivial if you live in flat space. Okay, but then of course we want to think about the generalization of that construction to curved spaces. Well, straight lines in R2 are curves which present the shortest distance between 2 points. Straight lines. Okay, And so when we come to curves in surfaces which are curved, okay, we'll be talking not about straight lines, they won't fit into the curve, but we'll talk about geodesics, okay, curves of minimal distance or curves of maximal straightness, okay. So that's what we're in the direction we're going to go. Straight lines are the geodesics on the plane R2. Given a point P, there's a geodesic in every direction. Well, in a plane, that's obvious, right? Here, I can go in that direction. I can put a straight line in that direction. I'll put a straight line in that direction. No problem. Okay. We want to generalize that concept to spheres, okay, hyperbolic geometries, and then general curved surfaces. And we'll learn a lot by doing that. Triangles are the building blocks of closed regions. Okay, we learn about the geometry of closed regions because you can make arbitrary closed regions out of triangulated regions. So here's a triangle in the red here with a vertex here, a straight distance here to the vertex I, up here to another vertex and back to where it started. Well, we notice, of course, that as we come to this vertex I, that the tangent to the triangle curve takes an abrupt change, okay, through the angle theta sub I over here, from the tangent before to the tangent after. At vertex I, t rotates to an angle theta sub I. The tangent turns through 2 pi radians as the triangle is traversed, right? The tangent heads in this direction, then this direction, then this direction. By the time we get back to the original spot and come around that vertex, it's back to its original position. And so it's turned through a total angle of 2 pi. So theta 1 plus theta 2 plus theta 3 is 2 pi. Okay, well that's sort of trivial, and it teaches us what the interior angles of the triangle are. Okay, because then these exterior angles, theta I, are related to the interior angles by this statement. Theta is equal to pi minus phi. And so if the sum of the thetas is 2 pi, then substituting in here, I learned that the sum of the interior angles of the triangle is pi. Well, that's something, of course, we learned in grade school, that if we have a triangle on the plane, that the sum of the interior angles is always pi. Okay. Well, that's a simple idea. And we're going to ask what the generalization is when we turn to geodesic triangles on curved surfaces. Okay, that might have some surprises for us. In particular, in doing this, we'll learn about Gaussian curvature, we'll learn about the Gauss Bonnet Theorem, we'll learn about holonomy. Okay, we'll learn about the rate of change of tangent vectors as you go around closed paths. So this exercise, which looks very innocuous and very simple, has to be generalized to surfaces with a non-zero curvature, and then we're going to ask, well, how is this changed when I come to those situations? Well, that's something we can look forward to. Okay, well, one of the first things we realize is the idea of congruence and similarity in geometry. When we're on the plane, the statement that phi 1 plus phi 2 plus phi 3 equals pi has nothing to do with the size of the triangle. Right? If I'm on a plane, I could take a triangle like this and a triangle like that, and they're similar triangles, and for both of them, the sum of the phi's will be pi. Okay, and it has nothing to do with scale. There's no scale in the Euclidean R2. Okay, but what about curved spaces? Okay, well, curved spaces are going to be different from flat spaces because there's going to be a new dimensional parameter here, and that's the Gaussian curvature. Okay, the Gaussian curvature. So there's an intrinsic scale in the surfaces which tells us the difference between short distances and long distances. We'll find that here, if two geodesic triangles are similar, then in fact they are congruent. Okay. There's a natural scale in the problem. Unlike R2 where you can have similar triangles on every scale, that's not the case. If you have geodesic triangles on the sphere, we'll check that soon, and it also will generalize to geodesic triangles on a generally curved manifold. Okay, if two geodesic triangles are similar in that broader context, they'll typically have to be congruent. Okay, we'll show that in the case of spheres, and then later we'll come back and we'll show that in the case of hyperbolic geometry, spaces with a constant Gaussian curvature which is negative. Okay, for Riemannian geometries, the Gaussian of small separation, small compared to 1 over the square root of kappa, is well approximated by Euclid. Okay, that's going to be one of the important features, okay, that we're going to learn from differential geometry. Okay, and it's particularly important for physicists, maybe somewhat less so for mathematicians, but very important for physicists. Okay, because we want to know the scale of phenomena in doing physics and doing physics experiments and understanding the physics of black holes. We have to know, okay, the difference between short distances and long distances. And in the case of classical differential geometry, the scale is set by 1 over the square root of the Gaussian curvature. We don't know that yet. I'm just saying, okay, that's going to come out, and it's going to be quite interesting. Well, we've seen that in the case of curves in R2. Okay, that the curvature of a curve in R2 was given by kappa, and that that showed us for distances small compared to 1 over kappa, okay, the tangent was a good approximation to the direction of the curve, but for larger distances the deviation of the curve from the tangent was significant, and we had to think about kappa. In the case of surfaces, okay, the Gaussian curvature carries the dimensions of 1 over a length squared. Okay, so 1 over kappa, okay, is a length squared, and the square root of it is a length, and that length tells us that the distance is less than 1 over the square root of kappa. Okay, the space is well approximated by Euclidean geometry, but for distances large compared to that, the space is highly distorted, and we're going to learn about that. Okay, we'll see that the second fundamental form of classical differential geometry tells us about that idea. Okay, so that's as much time as we have for today, and next time let's talk about other features of